Vibration analysis. What is phase? Understanding wave relationships in mechanical vibrations. Understanding phase in vibration analysis. Phase in vibration analysis refers to the timing relationship between two periodic signals, typically expressed in degrees across a 360-degree cycle. It is a critical concept for diagnosing machinery faults, balancing rotating components, and understanding structural dynamics. Unlike amplitude and frequency, which describe the magnitude and repetition rate of vibration, phase provides insight into how two signals align or differ in time. For example, two identical signals can have the same amplitude and frequency but differ in phase, meaning one signal reaches its peak later than the other. This difference can indicate whether components are moving together, in phase, or in opposition, out of phase. Phase analysis is essential for determining relative motion between machine parts, identifying misalignment, looseness, or resonance, and planning corrective actions. In advanced applications, phase data helps create mode shapes and visualize machine behavior under dynamic loads. Understanding phase also requires familiarity with measurement techniques such as using tachometer references, stroboscopic visualization, and dual-channel analyzers. These tools allow analysts to capture phase angles accurately and interpret them in the context of machine health. Ultimately, phase is not an isolated metric but part of a comprehensive vibration analysis strategy that combines amplitude, frequency, and phase to diagnose and correct faults effectively. In-phase versus out-of-phase conditions. When two signals are in phase, their peaks and troughs occur simultaneously, indicating synchronized motion. In rotating machinery, this often means components are moving together without significant distortion. Conversely, out-of-phase conditions occur when one signal reaches its peak while the other is at its trough, typically 180 degrees apart. This scenario suggests opposing movements, which can lead to mechanical stress and faults such as misalignment or looseness. Phase differences can also occur at intermediate angles, such as 90 degrees, which may indicate complex dynamic behavior or coupling issues. Understanding these relationships is crucial for diagnosing problems accurately. For instance, if two bearings on a shaft exhibit a 180 degrees phase difference, it may point to angular misalignment, whereas a 90 degrees difference could suggest unbalance. Analysts use phase measurements to confirm these conditions by comparing vibration signals from different points on the machine. Visual tools like bubble diagrams help represent these relationships, showing phase angles as directional vectors. Recognizing out-of-phase conditions early allows maintenance teams to prevent excessive wear, reduce vibration severity, and avoid catastrophic failures. Advanced analysis may involve correlating phase data with amplitude and frequency trends to build a complete picture of machine health. Where does phase come from? Origins and measurement of phase. Phase originates from the Role of tachometer in absolute phase measurement. A tachometer provides a measuring phase between 2 points. Relative phase measurement. Representing phase data, bubble diagrams and visualization techniques. Phase data is often represented using bubble diagrams, which provide a clear visual summary of phase relationships across multiple measurement points. Each bubble corresponds to a location on the machine, with a tail indicating the phase angle and the bubble size representing vibration amplitude. Standard conventions assign 0 degrees to the upward position or 12 o'clock, 90 degrees to 3 o'clock, 180 degrees to 6 o'clock, and 270 degrees to 9 o'clock. This format allows analysts to quickly identify patterns such as in-phase or out-of-phase conditions, which are critical for diagnosing faults like misalignment or looseness. Bubble diagrams can also include amplitude values inside the circles for additional context. In advanced applications, these diagrams support mode shape analysis and resonance verification by illustrating how different parts of a structure move relative to each other. Accurate documentation of phase data using bubble diagrams enhances communication among maintenance teams and provides a valuable reference for future troubleshooting. Software tools often automate this process, generating diagrams from collected data to ensure consistency and reduce interpretation errors. Stroboscopic techniques for phase analysis, measuring phase with a strobe. A strobe light can be used to measure phase visually by flashing at the machine's running speed, making the shaft appear stationary. This technique allows analysts to observe reference marks such as keyways or set screws and compare their positions at different measurement points. When the strobe is synchronized with the tachometer input of a data collector, it serves as a phase reference similar to a touch pulse. Advanced strobes can operate in external mode, where they track the vibration signal and adjust flash rate automatically, or in lock/track mode, where they follow speed variations to maintain synchronization. Some systems allow the data collector to drive the strobe, ensuring accurate phase tracking even under fluctuating speeds. Visual phase measurements using strobes are particularly useful for confirming analyzer readings and diagnosing faults in real time. However, safety precautions are essential because the shaft is still rotating despite appearing stationary. Stroboscopic methods complement electronic phase measurements, providing an intuitive understanding of machine dynamics and aiding in tasks such as balancing and alignment. Integrated phase measurement systems, data collector driving the strobe or vice versa. Modern vibration analysis systems often integrate data collectors and strobes to enhance phase measurement accuracy. In one configuration, the strobe receives input from the vibration sensor and adjusts its flash rate to match the machine's running speed, enabling visual phase tracking even under variable conditions. Alternatively, the data collector can control the strobe by locking onto the dominant one-order vibration frequency and driving the strobe's flash rate accordingly. This setup ensures that phase measurements remain accurate despite speed fluctuations, which is critical for balancing and diagnostic procedures. Integrated systems also allow analysts to perform visual phase checks alongside electronic measurements, improving confidence in the data. These capabilities are particularly valuable in advanced applications such as operational deflection shape analysis and resonance testing, where precise synchronization is essential. By leveraging the combined functionality of data collectors and strobes, maintenance teams can achieve higher diagnostic accuracy, reduce downtime, and optimize corrective actions.